Hey everybody, so we're going to be starting a brand new chapter today. We're going to be talking about exponential growth and decay functions, okay? And we'll hopefully get to see how they relate into a real world scenario. Granted, they're small scale, but it gives you an idea of how we utilize these equations within the real world. Now, the first thing we have to understand is exponential growth and how it looks on the graph, what its domains and range are, and then also the flip side, exponential decay and its domain and range. Alrighty, so let's get started. So for an exponential growth function, you're going to notice that e is going to grow. Oh, I've got my pointer. There we go. He's going to grow like this, okay? Now you'll notice he's not going to pass the x-axis. The reasoning for that is because there's an asymptote there in which he cannot pass. He cannot cross it. Now, in terms of how we describe the function, we like to describe the function as y is equal to a times b raised to the x power. Okay? So that's a times b with b being raised to the x power. Now, we also like to say that b is going to be greater than 1. The reason for that is if b was, anything, if it was just the number 1, you don't have any type of growth because multiplying anything by 1 keeps it the same. So in order to have growth, or even decay for that matter, it has to be something other than 1, right? Now, the domain is really simple. It goes from negative infinity to positive infinity, right? And then we also can say that the range, okay, it goes from 0 to positive infinity. Now you'll notice I did not say, includes 0, right? Because an asymptote, you can't include it. Now the asymptote is y equals 0, right? Now, looking at this next one, decay, it's basically the opposite. So we are now going down like this, okay? Like I said, it's the opposite. And so we still have the same function, y is equal to a times b raised to the x, but instead of b being a number greater than 1, it's got to be a number less than 1. But it has to be greater than 0 though, because if it's 0, then you have nothing at that point. So the value of b has to be greater than 0, but less than 1, okay? Now, the domain is the same, and so we have negative infinity to positive infinity. The range is the same. It's going to be from 0 to infinity. And then we have the asymptote is the same, y equals 0. Okay? Now, that right there, okay, is the standard form for the exponential growth and then the exponential decay. Now, let's go ahead and look at some examples here. So we're going to tell whether the functions represent exponential growth or exponential decay. So for example, say I were to give you this one right here. Y is equal to 2 raised to the x power. Well, in this scenario right here, a value is 1, right? A is 1. Because that's what's the imaginary number in front of it. But what is the b? Because that's what the most important thing is. What is b? Well, b is 2. Well, we can write it like this. Since b, 2, is greater than 1, y equals 2 to the x is an exponential growth, right? Is exponential growth. Now, I could also say something like this, okay? Say I had y is equal to maybe 3 and then 0.25 raised to the x power. What is this going to be? Well, a is 3, but what's most important is the b value, right? Since the b value is less than 1, but greater than 0, we have an exponential decay. So, since the 0.25 is greater than 0, but less than 1, it's going to be exponential decay. All right. So that's something to get across, okay? And to kind of understand, because when we start going into these other models, that'll actually be very important to understand, okay? So let me go ahead, let's get to those models. So the first thing that we're going to base that standard form on is the exponential growth model. Now, the way we write the exponential growth model is like this. We like to say y is equal to a, and then we have 1 plus r raised to the t, okay, as in time. Now, looking at this right here, please don't misunderstand. I mean, we haven't changed the idea. It's just standard form is now representing actual things in the real world. And so this a is still a, and this 1 plus r raised to the t, that's still the b value raised to the x. It's just now we're referencing it in terms of time and the growth rate, and the a represents the initial value. And that's actually something to denote, is that this is initial value. This is growth rate. It's kind of hard to put that in there. This is the rate. Now that kind of makes sense because we denote it with r, and then the t, that's time. Okay, that's what that is. Now, the exponential decay model is very similar, okay? In fact, it's almost identical, but one subtle difference. Y equals a, and then 1 minus r raised to the t. Now you might be wondering, well, what's the difference between the plus and the r? Well, guys, remember what I said. I wrote those inequalities for a reason. For an exponential growth, you know, for something to be growing, what did it have to be greater than? It had to be greater than 1. That's why it's 1 plus r, because anything, if it was just 1, you don't have growth, you don't have decay. So it has to be 1 plus the r for there to be a growth rate. Now, if it is a number less than 1, but still greater than 0, which is the decay, that's where the 1 minus r comes into play. Now, we're not anticipating that 1 dip below 0. We're anticipating it to exist between 0 and 1 for it to represent the decay model. Okay, hopefully that makes sense. Okay, let me know if it doesn't. Now, let's take a look at this first example though. Okay, so looking at this first example, it says in 2000, the world population was 6.09 billion. During the next 13 years, the world population increased about 1.18%, okay, each year. Write an exponential growth model giving the population y in billions t years after 2000, and then estimate the world population in 2005, okay? So I'm going to kind of zoom in a little bit so I can kind of annotate for you. I'm going to bring out my handy dandy highlighter first. So the first thing we need to understand is the initial value, okay? So first and foremost, we start off with 6.09 billion, okay? That was the population in 2000. Now, during the next 13 years, the world population increased about 1.18% each year. Now, that word increased, that should have already tipped you off that this was an exponential growth problem, okay? Because we're talking about increase, we're not talking about decrease. Decrease would have been, you know, incentivized us using the decay model, okay? So once again, you got to key in on these features right here. Increased by about 1.8%, which indicates exponential growth. Now, it's kind to you. It says that it, you know, write an exponential growth model. Now, not every problem in the future will be as kind as this one, okay? So you have to use context clues. Now, it wants to know the population in 2005, not the next 13 years. So that's another thing a lot of students mess up on, is that people will take data, okay? Because I can take data over the next 15 years, but maybe I don't care about the entirety of the 15 years. Maybe I only care about the world population in 2005 because that's a key year that will help me make a business decision or something. So we need to figure out in what is the population in the next 5 years? So let's plug all that in using those models that we created up top. So I have y is equal to a 1 plus r raised to the t. Okay, so start there. Now, looking at this, we said our initial value was 6.09. Now, it wants us to keep it like that. We don't need to write billion, otherwise we'd have too many zeros. But then we have to figure out what the r is. Now, guys, you have to understand and have to remember how to communicate percent into a decimal. The way you do that is you move the decimal to the left 2 spaces, okay? So if I have 1.18, if I go 1, 2, then I have another 0 there, okay? So this means I have 0, 1, 1, 8, okay? Now, the t, we said that the t is going to represent the time, and that was in 5 years because they're basing it from 2000 to 2005. Now, when you go to calculate all this, y is going to equal, and if you plug it into your calculator, 1 plus 0.0118, and so that's 1.0118. Raise that to the 5th power and then multiply it by 6.09. That's going to give you 6.45. Now remember, if you do not write units, this number means nothing, because think about it. If I didn't write units, are you talking about 6.45 people? No, I'm talking about 6.45 billion. I'm talking about a billion people. Imagine if you messed that up. We're trying to figure out how much the food bank is supposed to bring, to San Antonio to make sure everybody gets fed, and you leave off the word million. The food bank thinks you only need to feed 6 people. You know what I mean? So you got to make sure you write your units. It's very important. So that was part A. Now part B, unfortunately, we would have to use a calculator to estimate. And what we would end up doing, just to kind of try to communicate how we would plug this in, is you would take your TI Inspire and you would go y, need to get my thing out. We got y is equal to 6.091 plus 0.0118. In fact, I would actually scrap that. If I were you, I would just do 1.0118, just add it already. And instead of putting t, you're going to put x, because the TI Inspire does not understand that you're trying to determine time right now. It only understands y and x right now. So inside your graphing section, you would type this in, and then you would look on your TI Inspire and estimate, okay, looking at your tracing feature, when is the population going to be 7 billion? And hopefully you come to determine that when t is equal to 12 years, or also known as 2012, that is when the population will be at 7 billion. Okay, but we would have to use a calculator. But also, there actually will become a point in time for part B where I actually can show you mathematically how to solve that. It's just for right now, I haven't taught you those tools yet. So for right now, hold off, because there is this thing where we can use an exponential, we can use a log to actually figure out what t is, but we'll do that later on in this section, okay? So let's go ahead, let's come over to here to where we have example 2. It says, the value of a car Y in thousands of dollars can be approximated by the model where t is the number of years since the car was new. So it actually cut off when I copy and pasted. It's cutting off a function that you're actually needing to be able to solve this. You need the function y is equal to 25 times 0.85 raised to the t power. Okay, you would not have been able to solve this problem without that, and unfortunately it cut it off. So with that being said, A is asking, tell whether or not the model represents exponential growth or decay. Well, let's look at the B value. What is the B value in this scenario? Well, it's 0.85, right? Well, is that a number greater than 1 or less than 1? Well, it's less than 1. So with that being said, part A, I would say it's decay. Reason being is 0.85 is less than 1, but it's greater than 0. So, I mean, easy enough, right? That's exponential decay. So part B, though, goes on to say, and let me go ahead and scroll up, identify the annual percent increase or decrease in the value of the car. So it wants us to kind of figure out, what is going to happen to the value of the car as time goes on. Well, we actually know a lot about what's going to happen. We're actually going to be using that 0.85. But remember something. This is something that's very interesting, okay? And, something to consider, it's kind of cool, is that where did we get that 0.85 from? Well, we got it from, and let me write this whole thing out. Kind of cool. If you look at this, guys, this is the function of the decay model, which is A times 1 minus R raised to the T. So you're like, wait a minute, Mr. Farmer, you're telling me this bit right here is 1 minus R? I'm like, you betcha. But when you did your 1 minus R, you got 0.85. Okay, kind of seeing what you're saying, Mr. Farmer. I kind of get it. And I'm like, don't worry, let's solve for the R. So we go ahead and we subtract 1 on both sides. And so we end up with negative R is equal to negative 0.15. But then you divide by negative 1 on both sides, and so then you get R is equal to 0.15. But I want to know, what is the annual percent increase, not the decimal increase or decrease. I want to know the percent decrease. And so to do that, you move the decimal 2 spaces to the right, and that gives you R is equal to 15%. So this right here, this car annually is losing 15%. So this is a 15% decrease in the value of the car. So you might be wondering, well, what is the 0.85% trying to communicate within this problem? So the idea behind the concept of, owning a car is that a car loses value over time, but it doesn't lose all of its value in one go. So in this scenario, this car retains 85% of its value each and every year. But if you retain only 85% of your value, that means you're losing out on 15% each and every year. Now that 15% gets smaller and smaller and smaller as the value of your car gets smaller and smaller and smaller, because the idea, so think about it like this, 15% of a million, if you type that into a calculator, that's a lot of money. But if you do 15% of 1,000, that's not a lot of money. And so the idea is the 15% in relation to the value of the car at that time will get smaller, but it's going to be losing it just at a constant 15%. Okay, so that's what the 85 is trying to communicate. It's retaining the 85% of its value every year. Okay, now part C is just like when you would have your TI Inspire, like in example number 1. So estimate the value of the car will be 8,000. You would basically type this equation right here into the TI Inspire, but make sure instead of saying T, make sure you put X, and then you would go ahead and see when will the car be $8,000. And from what I got T is going to be equal to 7 years. So in 7 years, this car will go from being $25,000 to $8,000 in 7 years, which is kind of sad when you think about it. You spend $25,000 and you have a car that's worth $8,000. Adulting, it's great. Alrighty, so let's keep going. Alrighty, so this says this is like the next part, like what if the value of the car can be approximated by the model. Identify, and the model was I should got cut off again. Let me pencil. Y is equal to 25 and then 0.9 to the T. Okay, identify the annual percent decrease in the value of the car. Estimate when the value of the car will be 8,000. Okay, so in this scenario right here, this car is retaining actually 90% of its value per year, which is actually significantly better, believe it or not. And so in order to figure this out, you would take this 0.9, okay, and it breaks up into your 1 minus r, right? Well, you subtract 1 on both sides, and you got negative r is equal to negative 0.1. So r is going to equal 0.1. And so then r is going to be a 10% decrease. Okay? It's going to be a 10% decrease. Now, it wants you to then go ahead and say, you know, when will the value of the car be 8,000? Okay? And I will leave that to you. I want you guys to try to figure it out. Now, of course, you're going to be plugging this in over here, but just make sure instead of putting T, what do you put? That's right, you put X. Okay? So that's it for this video, guys. Let me know if you have any questions. Alrighty, signing out.